we are going to be talking about things that have to do with measuring and comparisons and language models. In particular, I'm going to start with basically what I think is one of my favorite papers, which is really fun and has this basic idea of how can we compare language models. There's going to be a bunch of stuff in there, and it's going to lead us to think about translation a bit, which is what we wrote another paper on, how you can compare translation models. And that I think is gonna lead to a lot of discussion. And then finally, unlike that past talk, I'm also going to talk about something new, but that's going to be very work in progress. So I'm going to have to switch slide decks at that point anyway. That's also not going to be in the recording. So if you're watching the recording, I'm sorry, next time. All right, so let's talk about language models. First of all, let's motivate this work a little bit. A question we might ask is, do current language models do equally well in all languages? Can they deal with all sorts of languages out there? The answer to that, we claim, is going to be no. We can ask a more specific question, be like, okay, well, what kind of languages are harder for them? What kind of languages are easier? And we can, for example, say German versus English. In that case, German seems to be harder. That's pretty noticeable. But we can also ask new questions, and that's these two questions we kind of talked about in a previous paper. And so these new questions are the bulk of the contribution of this paper. Like, what about non-Indo-European languages? Languages that are not in Europe, are like Chinese. We'll find out it kind of depends. We also wanted to figure out, what is it about a language that makes it hard to model? Just as a correlational study, not as a counterfactual study, but just what kind of languages are hard to model? Is there something that unifies them? We find out, nah, it's rather technical. And finally, the sort of icing on the cake in that paper, and what I think is the coolest takeaway, is what about translationese? Is translationese easier or harder? If you don't know what translationese, we'll get into that at that point. It's going to turn out it's different, but it's not actually easier. All right, so this first block about language models, first of all, we're going to need to define difficulty. Like, what do I mean when I say it's harder to model German than it is to model English? We need to see, okay, well, what kind of models are we talking about, and what kind of languages are we going to be analyzing? And then we can do this study and look at, well, what is hard, and is there something about these difficult languages that makes them difficult, something that unifies them, something that correlates? And finally, answer the translationese question. So let's take a look at that. First of all, just so we're all on the same page, what is language modeling? Nowadays, in the past 2 or 3 years, that's become kind of a contention, a point of contention. I will use language modeling to really mean the sense of basically the past 50 years, where language modeling is a generative modeling of text, a probabilistic model for text, something that you could sample a new sentence from, something that, given an entire sentence, tells you how likely is that sentence. So this does not include BERT and other masked language models, which is why I'm a little bit mad that we all call them language models now. This is really the probabilistic idea. And usually the way this goes, if you have a sentence, I'm just going to show like a prefix of that sentence, just to keep the slide short, but imagine that was a whole sentence. Oftentimes we just break it down into like a left to right autoregressive prediction. So we predict the first thing, and the second one based on the first, the third one based on the previous, and so on. And so this is just a valid decomposition. It's just a chain rule of probability. But this turns out to be much easier to model, because now we only need to figure out how can we model the probability of an individual token given the entire history, the entire left history. And so the way we like to do this is with neural language models. So we have a lexicon, a vocabulary really, where we have a bunch of words in there. They have a spelling, and they are assigned an embedding. So just a real valued vector. And together with that, we can now do generation. Say you do it with a recurrent neural network, like an LSTM. The LSTM gives you a hidden state. You compare the hidden state to the embeddings, and you're like, all right, this embedding looks good. You sampled this particular kind of type. Let's say it was the type that is spelled V. You feed it back in, sample the next one, and so on. And so that's how you can do generation. One thing that's a little bit funny about this is that you might be like, okay, fine, but what about a new word? What if I find a new word in the wild that's not in my vocabulary? Like, how can I assign it a probability? It's going to have probability 0 under this model, right? Which is bad, because nothing in the real world has like probability 0. That's a little bit extreme. So we can say that this model is closed vocabulary. And the way we made it work with the hack in the past, and I mean the past really mostly like the first 40, 50 years of NLP, is by adding a new type to our vocabulary that is just unknown, has its own embedding, and we just replace all those weird, random, rare, or novel words with this unknown. And okay, great. Now we can run this. It has non-zero probability, and we can generate text. It might just have a few unks in there. Okay. So that was fine for a long time, but I think we are old enough to not do that anymore. And in fact, the things that we're doing today with language modeling that are actually like generation and stuff like Elmo, BERT style extraction of useful contextualized embeddings, unking doesn't really cut it anymore. So what is the word? You know, you might say, okay, well, maybe we should just do everything on a character level then. No need for unking, no need for words. That's great. But then I spell out T, H, E, and that's just really annoying. So we need something in between. And if you've paid attention to NLP in the past 4 or 5 years, you will have noticed that the community has kind of settled on subwords as the answer. That's one possible answer, like BPE, word piece, sentence piece, like UniGramLM. That's one possible answer. Maybe we'll talk a little bit more about that at the end of this talk. So this slide was made before that became the de facto standard, which is why it might seem a little silly now to say, like, what about BPE? Anyhow, that's modeling. We can generate things. And if we're open vocabulary, either by being purely character-based or using BPE or using whatever clever mechanism we devised in the paper that I stole the slide from, well, then we can generate all sorts of novel text. And we're going to come back to that in just a second. Okay. So are we all on the same page? If there's anything unclear, just ask it in the chat so we can get into that. Otherwise, let's see. Language models assign probabilities. And so probabilities, if we take like the negative log probability or negative log likelihood, it's the loss that we commonly use, it tells us something about the surprisal. It tells us how surprised is the model to see this sentence? How unlikely is it? And the surprisal really means how much information is in there. So maybe this sentence has this probability, and it says, if you take the negative log, that's about 5 bits. You could do this in English. Maybe you also have a language model trained for German. And you do this, now the sentence is a little bit less likely, a little bit more bits, a little bit more surprisal, more information content. That sentence might be really surprising, so you might have more information. And so if you do these kind of things, you're like, okay, great. You are literally just comparing English apples to German oranges. That's completely useless. How are we going to compare language models? We do need to do it on something that has the same topic, the same style, the same content really is what we want. And so the obvious solution is to take translations. So if these 3 sentences are all translations of each other's, like in this case, then it seems reasonable that maybe models should really be equally surprised to see these 3 if the models were trained on the same data, just in different languages. So specifically, the training sets for these models, in this case, these 3 models, are all the same size. They correspond 1-to-1 to those sentences, in this case, European Parliament sentences. And so we are sure that they should all be equally surprised by the content, the style, the topics that appear. And it's really only the language that is different. And so in this case, we would see that, yeah, they assign roughly the same probability, but still it seems a little bit more surprised by English, a little less surprised by German in the case of this one particular sentence. So that's what we're going to be building this on. Okay. So it really matters that we have translation. And of course, translations are not that easy to come by, in particular translations that are shared across a number of languages and not just 2. So we've used the European Parliament data in the past. That's 21 languages. A lot of data shared, but not very many languages, and really a heavy Indo-European focus, obviously. And in this work, we've expanded this to 62 languages using Bibles. Still, it's not as much data, but it's the best we can do. You might say, whoa, the best we can do? Aren't there like hundreds of Bibles out there? If you've taken a look at those, you will realize that many of these Bibles really are only New Testaments. And it gets worse. Aligning them all across languages incurs so much loss that really there is not a single verse in the Bible that is shared across all the languages for which we have Bibles. And so we need to select like a number of languages that is as big as possible, that also shares as much verses as possible. And that's a crazy optimization problem, which was super fun to do. We did it with an ILP. If you don't know what an ILP is, you must be born after the 2000s, or you were like me before I started this project. It's really fun, and you can check it out in the paper. Anyhow, we selected a bunch of data. We ended up with 69 languages. This was not on purpose, but it is very nice. And so with that, we can now evaluate what we're going to want to do. Yeah, is the Bible a good data set? That's a great question. Thanks for that. I really don't think so. It is really a bit messy, and we're going to see something interesting when we get to the results in the second part of this talk. All right, so stay tuned for that. The second issue we're going to have is, I kind of said, look, we can compare the probabilities, the bits. Okay, great, but we really need to be careful here. In particular, we need to use the total number of bits of an open vocabulary model. Okay, why does that matter? Why can't we do other things, right? So first of all, why do we need to be open vocabulary? We can't use uncs because every unc is cheating. Every time you predict, oh, this is unc, you're like, yeah, this is right. It was indeed an unc. But like, wow, what kind of unc was it? What kind of word was it? This is cheating. And the issue is that morphologically rich languages, languages that have a lot of types, they are going to have more uncs because words are less likely to have been seen during training. So that will be unfairly advantaging them. So we should expect to see Czech doing like a lot better, for example, if we allowed unking. And so that's an issue with some other studies in that space. The second one is that I talked about total bits as opposed to something like perplexity, which might be the metric that you're familiar with if you've seen language models. The issue is that perplexity is usually given like in terms of like per word or per characters. Or like when we talk about perplexity, we usually mean like per prediction token, so usually per word. And that turns out to be an issue if we want to compare across languages, because languages build their words very differently. Let's take this example here. This is the same word. These are clearly cognates, putsch and Czech and in German. They really should be equally likely, right? If we have a model and it says, how likely is it that someone wants to say this like see in putsch, which in English is like coup, they should be equally likely, right? So they should be equally difficult. But if we normalized per character, then German would look a lot easier because there's a lot more characters to spread your uncertainty over. And so that's why we just need to take the sum of it all. How much information is contained in the entire sentence? What is the probability of the entire cross-linguistically aligned utterance? So we can do that with our setup. That's not too bad. Just need to make sure to be aware of that. Okay. So we've seen this example here that was just 3 individual sentences. How do we go from these few sentences to like a score for a language? You might say, okay, well, just average them and you'd be right. That's the thing to do. But we're going to make it a little bit more complicated, and that's not going to come in handy just yet. It's only going to come in handy in the second part of the talk. Okay, but bear with me. That's the last thing we're going to talk about in this part. If we have this fully parallel corpus, let's say in this case there's 3 languages, there's like 4 sentences in it, it's aligned, great. We can run our language model on each of these, right? The English language model on the English sentences, the German language model on the German sentences, and so on. And we obtain a bunch of surprisals, a bunch of information content. So in this case, I've kind of tried to draw this such that sentence 3 is like, looks kind of difficult. Maybe it's just very long. German looks a little bit more difficult than English and Bulgarian. Okay, fine, something like that. And so we could just sum them or average them. I mean, same thing really, and that's fine. But what if our matrix of sentences had holes? What if there's missing data? Like we could still just sum or average them, but it clearly doesn't make sense to, if you like average across all the languages, well, German and Bulgarian are going to look hard because they have this really hard sentence in them, whereas English got off easy. So we need a mixed effects model to model these things, a mixed effects model to estimate not only the difficulty per language, but also sort of the inherent surprisal, inherent uncertainty or length of an utterance that is going to be shared across all languages. And so our idea is, our model is that the surprisal we observe, the information content we observe, must be a product of the inherent difficulty of a sentence, the inherent length of the sentence, so to speak, and the difficulty of the language. So this is a probabilistic model. We put some log normal noise on it, but whatever your favorite distribution is that you want to do inference in. And so that allows us to not only get like one best estimates, but also do some sort of uncertainty stuff. And in fact, we got even crazier. We built a model that was heteroscedastic, a fun word I learned during doing this, that I now see everywhere, and every time it like warms my heart. And before you take too much of a look at these equations, just know that it turned out to be absolutely useless. It really didn't make a difference. So if we have full data, averaging is just fine. That's perfectly fine. And if we have partial data, that simple model gets you far enough. You probably don't need the heteroscedastic one. But we had to try, didn't we? All right. Oh yeah, I was going to show that. This is one of those slides. So like heteroscedasticity didn't really make much difference. Being all Bayesian and putting good priors on things and choosing a log normal distribution with good didn't really matter. Doing actual like marginal inference instead of just looking at map solutions didn't really matter. So I was pretty miserable when I realized that all this work was for nothing. But I learned something, and if you read the paper, you can too. Anyhow, that is really all that I'm going to talk about for this first part, which is, yeah, what are we even talking about? What is the difficulty of a language model?